Good afternoon and welcome to this webinar of Euro-Mediterranean Center on Climate Change. Today's webinar is going to address the modeling of hail probability of Italy using a machine learning approach. My name is Jaroslav Mysiak. I'm the director of the research division, risk assessment and adaptation strategies. And our speakers today are Verónica Torralba, who is a postdoctoral researcher originally coming from the Earth System Services Group at the Barcelona Supercomputing Center, now working as a postdoctoral researcher at CMCC, the Climate Simulation and Prediction Division. And the second speaker today is Riccardo Henin, who comes originally from Earth System program at the University of Lisbon in Portugal, and since about 1 year he joined CMCC as the postdoctoral researcher as well. Before we pass the floor to Verónica and Riccardo, let me a little bit introduce who we are, what we do. The Euro-Mediterranean Center on Climate Change is basically a multidisciplinary research center in Italy, working on basically starting from climate simulation at a large scale with the global circulation model through the regional climate models up to assessing the impact on society, on agriculture, on other economic sectors and nature. So our mission is to model and model climate system and its interaction with society and provide a reliable, rigorous and timely scientific results for policy and decision making. We are located all over Italy. We are organized in form of research divisions, and those research divisions are located across different cities in Italy. And the CMCC is one of the key provider of Copernicus seasonal forecast. We are doing also the Mediterranean monitoring services of Copernicus. We are running and coordinating the competence center of the European Environment Agency, which is called European Topic Center on Climate Change, Impact, Vulnerability and Adaptation. And we are also a focal point for IPCC in Italy. Through our research and innovation, we are advising European Commission, different Directorate Generals, national government, regional and local governments, as well as business entities. So we are organized in nine divisions. Advanced Scientific Computing division is located in Lecce and is dealing with supercomputing and the infrastructure research and modeling infrastructure. Our speakers today are from Climate Simulation and Prediction division, which is located in Bologna. And then we have two divisions: Economic Impact of Climate, Economic Analysis of Climate Impacts and Policy, and Risk Assessment Adaptation Strategies are located in Venice, in Italy. Impact on Agriculture, Forest Ecosystem Services division is located in Sassari, in Sardinia, and in Rome. In Ocean Modeling and Data Assimilation is located also in Bologna together with CSP, and Ocean Prediction Applications is located in Lecce in southern Italy. And finally, Regional Models and Geohydrological Impacts is situated in Capua in southern Italy, and Sustainable Earth Modeling Economics in Milan. So those are our topics, those are our divisions. We're looking into a number of policy relevant fields. We're looking into impact of climate change on cities and coast, including how cities might transform themselves towards climate neutrality, looking at future Earth, oceans, energy provision, jobs and growth, poverty and migration in Europe and outside of Europe, water, food and land use, social vulnerability, and and the root of vulnerability in inequalities, and so on. And this webinar is part of our outreach activities. We have a very rich program for dissemination and outreach, which you can check on our website and explore the wealth of communication channels and formats that we are maintaining. Very quickly, you can post questions and answers, questions throughout the webinar anytime. You just use the facility of Q&A and post a question, or you might raise the hand and then we will try to unmute you if this is possible technically. But in any case, please post your question in the Q&A session. So this is basically the housekeeping rules. And now, without further ado, I invite Verónica to take the floor and introduce the presentation.
Can you see my screen?
Not yet.
Okay.
Now we can see it.
Okay, perfect. Thank you. Thank you very much for the introduction. As has been said before, in this presentation, we are going to describe a hail model that is based on a machine learning approach that has been constructed just to explore the long-term variability of the hail conditions over Italy. We want to thank Antonio Cantelli, who has been actively involved in the development of the hail model, and also to Enrico, Stefano, and Silvio, who has been also contributing to this work. The presentation is going to be divided in two main parts. First, I will make an introduction of the work, just showing the motivation of this. Also, I will describe the databases that we have used. I will make a brief description of the hail conditions in Italy, and we will try to understand which are the environmental conditions linked to the occurrence of hail events. Then Riccardo will make an introduction of the hail model with the methodological details, and then he will explain the main results and conclusions of this work. As you already know, hail is a meteorological phenomenon that can have impact in our daily lives, as it is affecting different, for example, the roofs or windows in our houses, but also our cars. So this is an important phenomenon, but this is also affecting different industrial sectors, as for example, it can be the insurance companies or the agriculture, as it can produce damages in the crops, or even in the renewable energy sector, as very high hailstones can damage the solar panels, and this can lead to a problem in order to produce solar energy. So due to all these impacts that hail is having in different sectors of the society, the research of hail is quietly active nowadays, and there are studies that are trying to better understand the physical mechanism involved in the development of hail, but also some other studies that are trying to infer the economic losses that are associated to these kind of events. Until now, there are different observing systems that have been used for the identification and detection of hail events. For example, the traditional, satellite data, also radars and remote sensing. But some other examples are the hail pads that are useful to provide information on the hail conditions in the ground and also the hail diameter. And also we know some indirect sources of observations from hail that can be the insurance claims or even media reports. Despite of all these kind of observing system, nowadays it's still difficult to identify an observational database that can be comprehensive, and this has been prevented a more in-depth research of the hail phenomena in general. Particularly, Italy is a region that is strongly affected by the hail risks. Here I have included a few examples, but the event that took place 2 years ago that was affecting Bologna and was producing some problems in the cars, also in the buildings, was raising the interest of the insurance companies, for example, in having more information about the hail conditions over this country. In this context, if we compare the conditions in terms of hail, for example, here with the probability of hail in the Italian country, we compare with other regions over Europe, you can see that here we have a maximum probability of hail, but hail events are not only observed in this northern part of Italy, we can observe hail events in all the country, but until now there are some problems in order to provide good information or even forecast of hail, because hail is a phenomenon that has a very local nature, and also the time duration of this event is quite short, so this is a very big challenge. Also, the lack of a national observational database of hail has prevented a more comprehensive analysis of the hail conditions in this country. So in this work, our main goal is to develop a hail algorithm that can be used to estimate the hail probabilities for a long period. In that case, we have used 40 years, and for a spatial resolution of around 30 kilometers. This work has been developed in collaboration with Generali, which is an important insurance company that is interested in this kind of information just to be integrated in their decision-making processes. As I have mentioned before, there is a wide range of, there are some limitations in the observations, and this also has prevented to have a comprehensive analysis of the hail conditions in the European countries. In this map, this variety in terms of the studies can be observed as the spatial resolution is different. Also, the kind of indicators that are explored in every country or region are different, because some studies are more focused on climatological values of hail. Some other studies are more focused on the diameter of the hail events, as this is an important factor to understand the severity of those events, and also the observations they are using, or it's quite different, and the time periods they are using between all the different regions. So it's difficult to provide a comprehensive analysis in the comparison of the hail hazard between different regions. However, the large scale variables that can be promoting the development of hail are similar in all the places. So this property has been exploited for the development of hail models that can provide information not only at the regional level or at the country level, as for example in this paper that was done for Italy, but also just to provide more information at the continental level, as this work for Europe, or even at the global scale. Some of these hail models that are based on the large scale variables are trying to combine those variables by using different techniques. For example, the multivariate methods involving principal component regression or partial least square regression, that are techniques that have been widely applied in the climate context just to understand the link between different variables. Also some basic or logistic Poisson regression model, more complex black box models that can be based, for example, on rainforest approaches, and also some models that are based on algorithms that try to identify which are the empirical relationship between this kind of larger scale variables and the hail conditions in specific locations. Between all these approaches, we have used this work from Prein and Holland as a reference for the development of our hail model for Italy. And this model was developed to provide a hail probability at the global scale. And we have selected this as our starting point because it has high flexibility, as it relies only on reanalysis data, which has this global coverage, and also 40-year period with a high temporal resolution. Also, it's not considering any specific distribution of the variable, which can be a problem as depending on the predictor that we can use, this can be a limiting factor. And also it's not prescribing any link between different variables. So all these properties make this model quite interesting to be applied for our particular problem, that is just to provide information for Italy. The main challenge in the development of this model is the selection of the most appropriate variables that can be used as predictors in the hail model. So in order to do this in a systematic way, we have employed a genetic algorithm that allows to determine which are the most important variables to describe the hail conditions over Italy, and also it can be used to estimate some parameters of the model. About the databases that we have used, we have considered the European Severe Weather Database that is providing information on the hail events with the specific location, also the time, and for some events is including also the diameter of the hailstone that can give some guidance on the severity of the hail conditions. This database is covering a period between 1996 up to 2020, but we have only considered the period starting in 2000, as before that the number of hail events for Italy, it was very, very limited. The European Severe Weather Database is particularly constructed with observations from volunteers. So they are giving all this kind of information and contributing to the development of this database, but also from media reports or from the weather services. For the evaluation of for the development of the hail model, we have used the ERA5 reanalysis that is having hourly resolution and the spatial resolution of 30 kilometers, which is quite good compared with other state-of-the-art reanalysis products. And we have selected all these variables that are listed in this table just as a potential predictors for our hail model. The criteria for the selection of these variables are two. First of all, we have considered some variables that have been already employed in other studies for the development of hail model, and in which we have seen that there is some link with the hail conditions. And also, we have tried to take into account the ingredients that are necessary for the development of a hail model. For example, having high convective energy, having wind shear, and also some lifting mechanisms necessary to overcome the convective inhibition. So using this criteria, we have 19 variables that have been considered for our model. Here you can see a summary of the hail data that is found for Italy from the European Severe Weather Database. We can see that most of the hail events are located in the northern part of Italy, which is linked with the orography of the country and also with the position of the upper level jet. And for this analysis, we have considered not only all the hail events that we have, but we have created a new category just to have all the hail events with a diameter above 2.5 centimeters. And this is a threshold that can suggest that this hail can produce damages in different infrastructure and also can affect different sectors. Here we have done also an aggregation of these hail observations to the ERA5 grid, just to have information of hail that can be used to evaluate our model and also to explore the links with the ERA5 variables. Another property that we have been exploring that from this hail data, well, some things have been summarized here in these plots. For example, the number of events that we have per year. You can see that from 2009, the number of hail events is increasing, which is a promising result because it's suggesting that maybe in a few years we will be able to have more hail events that can be used for a better understanding of the hail conditions in specific European locations. But this increase is mainly due to the higher engagement of the volunteers in order to contribute to the database. Also, we can see that in terms of the daily cycle, most of the hail events over Italy happen in the afternoon between 2 and 3. And also that most of the hail events are concentrated in June and July, in general in the summer months. If we were to evaluate which is the peak month, so the month in which we have the highest number of hail events in the 2000 to 2020 period, you can see also that June and July are the most important months. But we can see also some events, for example, in April or even in October. So for that reason, our hail season is usually considered between April and October. The next step for this analysis is just to understand which is the link between these atmospheric variables or convective indices with the specific hail conditions in the Italian domain. In order to do this analysis, we have considered each one of the ERA 5 variables that were represented in the table I showed you before, and we selected these variables for each specific time step, like 6 hours before and 6 hours later, the hail event. And we have summarized the median for each time step in this plot. These variables have been selected in the grid point that is nearest to the hail event, but we have taken into account also the sensitivity to this choice by considering not only the nearest grid point, but the area around the grid point that has been represented in this plot as a dashed line. You can see here, for example, that we have considered also two different categories. The dark blue is corresponding to the hail events with a diameter exceeding the 2.5 centimeters. And also and in the light blue color, we have represented the variables, the response of this variable for all the hail events that are not satisfying any specific condition. So you can see here that, for example, in terms of the convective available potential energy, which is an indicator of the amount of energy necessary for the development of a convective storm, we have that like 3 hours before up to the occurrence of the hail event, for the severe hail cases, CAPE was exceeding the 1,000 threshold, which is indicating that maybe this threshold is when we have this threshold, we have an environment that is favoring the development of severe hail. Still, for both cases, we can see that the CAPE values are much higher than the climatological values, so it's important to have enough convective available potential energy for the development of those storms that can produce hail. In terms of the convective inhibition, we cannot see so many differences between the severe and all hail events, but we can see also a minimum value that is observed just 1 hour before the occurrence of the hail event. And this is, in that case, when we have very low values on the convective inhibition, this is favoring the development of the convection, as this low threshold can be overcome and the storm can be formed. Another indicators that we have used and we have also included in our hail model is the freezing level height, which is the level in the atmosphere in which temperature is changing from positive up to negative values. And you can see here that these values are above the climatological values for the two different categories, and that for the severe events, the freezing level height is systematically higher than when we consider all hail events. This freezing level height should be in a balance, because too high freezing level height can lead to melting hailstone before they reach the surface, but too low freezing level height might limit the amount of supercooled water. So it's important to have specific values for this variable, as it can influence the development of the hailstorm. Also, wind shear is an important ingredient of the development of hail and is amplifying and sustaining the updraft through the storm organization. And you can see here that there is an increase of the wind shear just after the 1 hour before the occurrence of the hail event, but still we have wind shear conditions that are higher than the climatological value. Other two indices that we have considered are the K-index and the total index, which are widely used in order to estimate the potential for a thunderstorm to be developed. And these are based on the temperature at higher levels in the atmosphere. These two indices are quite similar in terms of computation and interpretation. And you can see here that, for example, 2 hours before and 2 hours later, both for the severe and the all hail events, the K index is exceeding this 30 Kelvin value. And something happened here for the total index, something similar, but in that case, our threshold is 50 Kelvin, because the indicators are slightly computed in a slightly different way, but still this is suggesting that these are the good conditions for the development of a hailstorm, and at least for the development of a storm that can produce hail. Also, we have considered these two indicators, which are the cloud base height and the vertical integral of the divergence of moisture flux. The cloud base heights are also under the climatological value for the two categories that we have considered. And this is because low cloud base heights can favor the deflection of cloud droplets. Also, in terms of the vertical integral of divergence moisture flux, we can see a peak just 3 hours before the occurrence of the hail event with a minimum. And this is linked with some previous knowledge on the link between this variable and hail, and it has been shown that just having highly negative values of the vertical integral of divergence moisture flux can be related to a precipitation intensification. So this is the summary of the analysis that we have done to understand the link between the atmospheric variables and hail. And now I think Riccardo is going to explain how this information has been used to construct the hail model. So the floor is yours.
Thank you very much, Verónica. Jumping into the screen. Okay, and just keep going with the presentation. So as you said, I'm going now to introduce the implementation of the hail model and to show some results in terms of maps of probability of hail for the Italian domain, and also the analysis of historical trends we computed for the probability of hail. This is just a workflow for you, for the audience, to better understand exactly which are the steps of this process. And to recall a bit the concept we have seen so far. So we have all the data on the left side of the screen. We have all the potential predictors that Veronica described before from the ERA5 reanalysis. And we have then all the observations coming from the European dataset. I added here also these sunny days. I'm going back to this later on. This is a category that was needed in order to feed properly the algorithm that is going to help us in computing the probability of hail. So we have three main steps in this process. At the beginning, we will characterize the potential predictors in terms of probability density function. So basically, we are looking at the typical range of values for each predictors from the climatological point of view, and also during the hail days. So when we have observations, then the core of the process and the core of this model as well is the genetic algorithm. So it's an automatic procedure that we need in order to define the probability functions we used to characterize the hail environments, and also to select objectively the best set of the potential predictors. With these kind of informations, we can then compute the probability of hail simply as a product of the individual probabilities. There's now at least one slide for each of these steps to go deeper on that. So we have been, Veronica mentioned before that this method is based on a probabilistic approach. In fact, we want to estimate the probability of hail based on the probability of each predictor. But so which kind of probability are we talking about? Basically, we want to define the probability that a certain environmental conditions that are defined by the range of values that a certain predictor can assume. We want to see whether these environmental conditions are favorable or not for hail formation and also for hail maintenance, for hail persistence. That's why we are looking at this kind of plot. This is just an example for K index. So this is a temperature, basically. We have something like this. So we have the black line that describes the climatology, the red line describing the distribution during hail days. And then what we want to do is to define a sort of slice in this plot, a certain range of values that we assume they are favorable for hail formation. So we will have like something like a hail and no hail, let's say, intervals. Because of course values lower than a certain threshold and values exceeding a certain threshold might not be useful for the model. We did this all this twice, and so that we developed two different models. The first one we call it general hail model because it takes into account all hail events, so all the hail observations, independently from the diameter of the hailstone. And then we also tested a severe hail model, so a model that applies only to severe hail events. And with severe, we mean that the diameter of the hailstone is greater than 2.5 centimeters. Again, about these functions. So these are hyperbolic functions that are formally defined, controlled by a total number of 5 parameters. These parameters are basically 4 percentiles that then, of course, they are linked to a specific values in the distribution of the variable. And by a smoothing parameter, see that simply define the steepness of the ascending and descending branch of the functions. So what we want to do is to, through this set of parameters, we want to define the blue line. So this probability. You see here the explicit definition of the explicit formula of the probability functions for the ascending and the descending branches. But again, we come to the question, so how do we choose the values for these parameters, and most of all, which meteorological variables to choose? Because as we have seen before, we have a total set of 19 potential candidates as precursors for hail events. I highlighted here in red these 3 parameters because, in fact, I mean, this is a system of equations that can be solved by knowing only these two parameters, and then we have the smoothing parameters. So we have a total number of 3 parameters to define that can be combined with up to 19 potential predictors, so that we have a very large number of free parameters for the model. And therefore, a grid search algorithm is not suited for that, and we eventually selected a genetic algorithm for this. The genetic algorithm is an optimization procedure that was formerly developed in biology, and is an optimization procedure based on the minimization of a fitness function. In this case, our fitness function is defined based on the Matthew correlation coefficient that is computed through this computing in this way, and basically it defines the ability of the model to predict a hail day versus a non-hail days. This coefficient takes into account all the 4 instances of the contingency metrics. Therefore, it is very robust, more than other standard metrics that can be used in this kind of optimization processes. Of course, we had to prepare a bit the data to feed properly the genetic algorithm. We had to aggregate the observations onto the ERA5 grid, as Verónica said before. We had to smooth the information space because of some potential inconsistencies, unmatching between the ERA5 data and the observations. And then we had to add these sunny days, because of course, if we provide to the model only the hail observations, the model will be able only to predict the occurrence of hail, but we have to provide also some information about the negative class. So we artificially, let's say, added some what we call sunny days, so days during which we had no precipitation at all over Italy. And we also keep an unbalanced ratio of sunny versus hail days in order for the genetic algorithm not to overpredict one of the 2 classes. Just very quickly about these genetic algorithms are pretty complex, and we need to provide also to choose some parameters. at the very beginning. So first of all, we limited the number of iterations to 200, and we also tested sometime for the population size we tested. We did a bit of sensitivity in order to find the best, the optimal number. I'm not going deeper into this, but just for you to know that, of course, we have to define, you have to guide a bit the algorithm in order to properly combine all the parameters we are giving it at the beginning. As I said before, this is based on this comes from biology. So basically all these values define how the model should mutate and do all the potential permutation between all the ingredients that we have. The results of this model is basically is twofold. So we have the finally the number, the variables, the predictors that we can use for the two different models. And also I'm not showing that because it's not very useful, but we have all the values for the parameters to define the probability functions. And then we are able now to compute the probability of fail. It's worth noting that there is a certain overlap in terms of which variables have been selected. For the two models, CAPE, freezing level height, total index, and cloud-based height do appear in both the models. And then we have for the general one, the boundary layer, and the vertical integral of divergence of moisture fluxes, and for the severe, the K-index and the convective inhibition. Wind shear do also appear in both with a different vertical extent. So eventually we are able now to plot these blue lines, so the probability function. You'll see here that you have the continuous line for the general model, and the dashed line refers to the severe model, only for those variables that do appear in both. And from this kind of plots are pretty useful and interesting because they allows us to also check by eye quite qualitatively, and also in case we can also quantify that the overlapping, the degree of overlapping between, for example, the distribution of the climatology and the distribution of the hail on the hail events. So, for example, this tells us which of the precursors can provide for a more added value, for more useful information. For example, CAPE and the convective indices, so K-index and total index, do have a small degree of overlapping between the two distributions. So we can consider that as very important precursors. And also we can see how these probability functions on these blue lines are drawn with respect, for example, with respect to these two distributions. I'm just showcasing other plot. This is the wind shear, the vertical integral of divergence of moisture fluxes, and the cloud-based height. Just to show you that for the 7 variables that have been selected for genetic algorithm, we have now all these probability functions defined. We can say that the probability function correctly identified the range of values that are typically associated with hail events. So they more or less cover the same range of values that are included in the distribution, in the hail distribution, so in the red line. And then this is also worth mentioning, compared to Prein and Holland, which is our reference, this distribution typically shows lower values for the variables. But this is something that was expected because this Prein and Holland model was optimized for the US. And we know that in the United States, the convective events are typically stronger than here, and they are often characterized by very extreme events like tornadoes or hurricanes. So this is just to show that it is very important for this kind of models to be tuned and to be optimized for the very specific domain of interest. So eventually we come to the maps for the probability of hail. So this map is showing it's a normalized map, first of all, and it's showing the probability of hail computed is the average probability of hail all along the year, where here, as when we say year, we intend actually the hail season, so from April to October, and computed all over the 41 years of data we have from ERA 5. The circles in the map represent the observations we had from the European dataset. And apart from this peak we have here in the plain of Piemonte, which is a kind of, this is a kind of outlier, and the way we normalize this map is somehow enhancing this point. What is important here is to see that on average, the higher values of the probability do cover all the Po Valley, and especially the lower part of the Po Valley. And also there is a clear signal along the Adriatic coast, plus some spotted area on the Tyrrhenian coast. And also what is important to say is that there is a pretty good fit between the hail observation, the number of hail observations we have, and the hail probability. I'm not sure if you can appreciate that, but here in Trentino Alto Adige, unfortunately, this not holds. But this is probably something that comes from the fact that we know, despite several attempts, the ERA5 resolution is not yet able to correctly represent the orography, and we have a pretty narrow valley here, so that's probably the reason why our proxies are not able to find a sufficient value for the probability of hail. This is the same map computed for the severe model. The pattern is more or less similar. We have very high values here on the coast between Veneto and Emilia-Romagna. And generally speaking, let's say the spatial pattern is a bit sharper than the general model, in the sense that the domain affected by severe event is somehow shrinked. There is still a general signal persisting on the Adriatic coast and some very few spots on the Tyrrhenian side. We have been checking also for monthly variability for this PDH. So these are, again, a normalized map computed in the same way as before for the 7 months. There is something interesting here, in our opinion, that is we have higher values in early summer in the north of Italy, early summer, and also in June, for example, in July. And the higher value in the south mostly occur in late summer and even in October along the coast. This is something that we can appreciate also in the severe model. Again, the signal here is even sharper. We also have that in the severe model, probability of fail is higher in the north of Italy, also in July and August. But this is something that, again, we could expect, because if there is a hail event in the truly summer months, it's more likely this event to be severe, to be extreme. Again, we have this peak in the south in September and October. Eventually, we also we also computed the trend over these 40 years. We computed the trend for the 99th percentile of the PDH obtained with the model. The statistical significance of the trend is computed through bootstrap methodology with 1,000 of iteration. And so what you see here plotted, like the color shades, the plot refers to those points where the trend is statistical significance with the 2 sigma of significance. So white areas represent places where the trend is not significant. We can see for both the models that there is a general increase of the PDH. What it is shown here, and that's why the values of the color bar is pretty low, is the slope of the trend. So it's the annual increase, the average annual increase of the trend, which is computed as a linear regression. And we see then, therefore, that there is an increase of the trend in all northern Italy and the Adriatic coast. And for the severe model, there are some signal of decreasing, kind of pool of decreasing trend here between Sardinia and the southern Tyrrhenian coast. As we did for the PDH itself, okay, here, just in case you want to see the information that is behind, these are the 10 series of the trend for 4 selected locations. 2 in the north, Milan and Bologna, where we had a pretty clear increase, and 1 in the south, Palermo, which is also increasing, even though the values of the PDH are generally lower, and then an example of a decreasing location in Sardinia. It's pretty interesting to notice that the step in this time series often occurs in the 90s, between the 90s and the year 2000. So most of the, let's say, the big part of the change occurs in this decade. As we did for the PDH itself, we also checked for the monthly trend. And this is pretty interesting because we see that there is a pretty clear signal of an increase of the PDH in the north of Italy in spring and early summer. And also there is a quite confusing pattern, I would say, in the canonical summer months, with some decreasing and increasing areas, especially in the center of Italy. And again, we have some increase in the in autumn in the south of Italy. This holds for the general model. We did that also for the severe model. And again, in this case, I would say the signal is sharper. It's more or less the same, but it's sharper compared to the general model. We can conclude now, just a few points. So we have seen at the beginning how Northern Italy, the main motivation for this research, that is that Northern Italy is one of the European regions most affected by hail damages. The impact has gained the attention of several economic sectors, insurance, first of all. And thanks also to the technological improvements, the number of hail reports has increased in the recent years because of increasing engagement of the people, of the crowd. And we have seen that most of the hail events in Italy occurs in afternoon and in the summer months, June and July. We have seen that there is a very wide range of potential variables and convective indices that we can use to characterize hail events. We have seen which of them has a strong link with hail events over Italy, and we have then selected with the genetic algorithm objectively those ones that can be used as predictor for the estimation of hail probability. We have developed, therefore, two models, one for general for all hail events and one severe only for events with hailstone diameter above a certain threshold. And we have been able to provide then for probability of hail all over the domain and over a 40-year period. The higher values of the PDH affect northern Italy in early summer, and whereas the maximum values in the south are observed, on the other hand, in late summer, in autumn. We have seen that the PDH is significantly increasing over most of the Italian domain, especially in the Po Valley and along the Adriatic coast. And these major increases are observed in early summer. And on the other hand, the decreasing signals are less coherent, we can say that. Eventually, the annual and seasonal trend patterns are sharper for the severe hail model compared to the general model. We conclude in this way. We thank you for the attention, and we are here for any potential question.
Thank you very much, Riccardo. Could you please leave the last slide for all the participants if they wanted to refer to that? And I would like to start with a question of Alexander Demin. He posted that some time ago, so we immediately go to that question. And the question is, as you have used ERA 5 data with roughly 30 kilometer resolution, Alexander says hailstorms are quite local in time and space, especially for the large hailstone events. So how important is the horizontal resolution in your algorithm, and how important is it for the accuracy or uncertainty of your results?
Okay, I have something to say about that, because, for example, I can go back a bit in the slide. Sorry, in the definition of in the genetic algorithm, we had in fact to take into account for this. If you notice, yes, I mentioned here in the table smoothing procedure. This is something that more or less is linked to this question, because we have noticed that sometimes there is a certain mismatch, for example, between the location, the observations, and the representation of the not the hail itself, but the convective systems that produce hail in ERA 5. Sometimes it's really a matter of 1 or 2 degrees, 1 or 2 grid points. And that's why, in fact, we did a sort of smoothing. That is basically we compute the PDH over also in the neighboring point of any specific grid point. So we did a sort of smoothing of the information coming from the reanalysis. Yeah, because we really saw for a couple of examples that we had the information in one grid point, but then, for example, the representation of the frontal systems, or I mean, or any other variables from ERA files, maybe the maximum for that variables was observed in the neighboring point. So this is something that usually also in Prein and Holland there is a sort of smoothing for this reason. I don't know if this is clear.
Yes, this is something that we have also taken into account for when we have been exploring the links between the variables and the occurrence of a specific hail events. We were testing the sensitivity to the resolution. That, of course, is maybe the resolution of 30 kilometers is quite hard to analyze a phenomenon that has this local nature. But we are trying to understand the general properties, and of course the output of our model is also based on this 30 kilometer resolution. So yes, of course, with this information we cannot say anything of detail on this, but just to extract this long-term information and variability that is also important for the mitigation of the hail risk.
Excellent. Thank you very much for to both of you for the exhaustive answer. Alexander, I hope the speaker have responded to your question in a satisfactory way. If not, please feel free to comment additional post or get in touch over email. I would go now to the question on Q&A facility by Valeria Aloisi, and she says, my question is related to the genetic algorithm. How does this algorithm manage to select the set of predictors of the model? Does it take into account eventual multicollinearity among the predictors?
Yes, this, the genetic algorithm is, let's say, an automatic procedure, is part of the, we can say, big family of machine learning approaches. As I said before, it was developed formally in the context of biology and of natural selection. So basically, the selection procedure is not random. It's not random as other optimization procedures, as it is in other optimization procedure. It's not random in the sense that there is an initial set, initial population, and in each iteration, the model computes the fitness function. And in the table, I go ahead one slide for you to, okay. So this elite percentage is referred to the size of they are called the gene because as it comes from biology, all the elements of the genetic algorithm is called genes. So you basically, after the first iteration, you select those genes, so those parameters that got the best score, the best J in this case. Those genes then basically constitute a sort of embryo, sort of nucleus, around which to do the mutation and the crossover. That is, mutation, it means that from one element you just try to switch the element in order to see again how the fitness function change. Crossover, it means that you generate, starting from two elements, you generate a new one. So I'm saying it's not random in this sense. So you have a sort of initial set that is the ones that in the first iteration has obtained the best score. And then from that, and that's why these parameters are somehow controlling the speed and the range of variability of this process. You add and you try to change the predictors in order to find eventually the best set, the best array, so the best set of elements, the ones that has the minimum value of the fitness function.
Thank you very much. That's excellent. We are getting many questions, and I'm trying to like cluster them according to the key topic of interest. So I would like perhaps to combine two questions from Gianluca and Agostina, and ask, the first is, about the hail probability. So do you assume that the different drivers or proxies that you are using are independent or not? If yes, can this be a limitation? So maybe meteorological drivers are related to each other, so they are not independent. So this is the one question, and I would combine that with the question of Agostina when she says, basically, have you considered the selection bias? Because there might be a reporting bias in your European extreme weather database. You might get perhaps reports from certain location, but not from the others. And she mentioned, for example, there is a high probability in Naples. So it's in your climatology, there is no hail probability in Naples. Why it's well known that you can have huge hailstorm even there. So to what extent the reporting bias, and that might be changing over the time, plays a role in your model.
Say something?
No, I mean, I think this is something that we have considered, just taking into account this information on the sunny days, trying to have this just because we needed something to evaluate the case in which we don't have hail, which is not only including the hail data that we had, but that is not still is very limited. We know that, but yeah, we try to consider another source of information to take into account how were these no hail events. Of course, this we tried just include a number to keep the balance between both categories, but still this can be maybe improved in some other cases, because there are different things that need to be tested on this. So yes, I mean, this is something that maybe we need to work a little bit more on this, just to refine a little bit the model to be more accurate in that sense.
Fantastic. You see that. I mean, there's a huge interest in hail hazard modeling, and this is confirmed not only by the number of the participants to this webinar, which reached in the peak exceeded 70, but also in type and number of questions that you get. So why the participant appreciate your work. There's some question about the methodology, possible shortcoming, possible improvements in the future, and so on. Another question from Valentina Pavan. She's asking, you have considered hail events in winter. Is it because you don't have observation, or because the model you use has not a sufficient predictive capabilities for winter months?
Well, that's because mainly, take the stage. That's because mainly we don't have hail events in winter. I mean, we considered the hail season from April to October, and as if you notice, in fact, there are very few hail observations even in April and May, almost. So yes, I mean, most of the impacts and most of the interest in hail events is referred to the summer season. So yes, that's mainly why. I mean, in fact, even most of the variables that we have considered, like CAPE, or I mean, they are useful in this sense, like in the sense of describing hail environment. Yeah, in summer.
There are a number of interesting questions, taking us a little bit far away from the topic of the webinar.
Yeah, latitude. Yeah, this latitude. We have to focus on summer, of course.
And also it's true that we have limited number of observations, of course, but we have limited number of observations also because the number of hail events that are registered for winter are much less, and of course the impact of those events. So for that reason, we decided just to be concentrated and calibrating and developing our model for the other season. But it's something that I think it can be extended also for winter.
I would perhaps pick up to this question from Francesco, who asked something about the way the genetic algorithms are set up and run. So why do generic algorithms need an unbalanced data set? between hail, no hail classes instead of a balanced one in order to work properly?
Well, that's because basically in the real world, in the real world we have an unbalanced number of hail days and of sunny days. So if we say teach the model, and if we provide the model not a reliable set of population, then the model tends to over-predict one of the categories. So we need to keep somehow this unbalance between the two classes, because that's how, say, reality works.
Mm-hmm. Excellent. Another question by Andrea Gatto again about the procedure. He's asking, considering that PCR is based on the principal component analysis, PCA, procedure, is there a standard methodology to set the threshold for the PCA?
Well, in our case, we have not applied those methodologies. I only put that methodology as an example of the kind of works that have been developed for combining these large scale variables in order to provide hail information. In fact, I think, well, maybe I can go to that slide specifically, because the paper from, oh, sorry. Yeah, in that paper from Excel et al. 2012, they are providing information for this small region here in northern Italy. And in that paper, they are using these methodologies just to combine the large scale variables. So maybe you can check this specific number about the threshold for the selection of the PCA in that paper, because I don't remember exactly how they were selecting that specific variables, and we have not applied this method here.
Mm-hmm. Excellent. Verónica and Riccardo, I would suggest you to go afterwards through the comments. Also, Alexandra posted an answer to your explanation, and he offered interesting insight as well from his own work. So there are a number of interesting feedback, but unfortunately, this is all we had time for. So at this stage, I would thank our presenters. They will get all your questions, and if they have any chance, if there is a email address connected to your name in a record, then they might get back to you. Some question about whether the slides and the recording will be available. They are available within few days from our YouTube channel of CMCC. So this is also communicated by our communication office. So don't worry, the slides and the recording is available. So Verónica, Riccardo, thank you very much for this extremely interesting talk and insightful discussion. Thanks to all the participants. As I said, I mean, outside is a sunny and warm weather, and staying with us means that there's a great interest into the topic and so on. So thank you very much. Thank you for the CMCC Communication Office for setting up this webinar. I have only one slide to announce. So Riccardo, if you could stop sharing. Okay. I would simply anticipate what is the topic of the next CMCC webinar. This is going to take place on June 30th at 3 o'clock in the afternoon, and it's going to address the sources of uncertainty in long-term global scenarios of solar photovoltaic technology. And you can see who is the speaker from University of Geneva, Mark Jackson Rosen, and we have a number of discussants and moderator from École de Bond from France. So this is our next webinar, and again, thank you very much, and have a nice day. Bye-bye.
Thank you. Thank you, everybody.